Okay, great. Let's start this morning. The first talk is by Achim Krause on the K-theory of Z-mod PTN.
All right. Yeah, thanks so much for the opportunity to speak here. So all of what I'm talking about today is joined with Ben Antieau and Thomas Nikolaus. And I think some of you have seen me talk about this before, or at least one of us three. But today I want to get into some aspects of this project that I think I haven't really talked about before. So usually I spend some time talking about like the history of K-theory computations. But since this is a p-adic conference, let's somehow cut like right to the meat. So what's special about these Z mod p to the n things? Well, for a ring which is key-complete and finite, such as this, p-adic K-theory, so the p-completion of K-theory, actually compares very favorably to some other invariants of rings constructed in homotopy theory, namely topological cyclic homology. So this cyclotomic trace map, which you always have, is an isomorphism for non-negative degrees. And there's like more general versions of this, but this is like a special case of Dundas, Goodwillie, McCarthy. So this guy called TC, that's still like a homotopy theoretic invariant. So it's not trivial to compute or anything, but it's somehow more approachable. So one way to think about it is that it sits in a sequence where it arises as equalizer of two other theories, negative topological cyclic homology and like some periodic version of that, TP. And there's a canonical and a Frobenius map here, and TC is the equalizer. So you can think of this as some kind of external version of a Frobenius. It's not quite an endomorphism, but this still somehow expresses this as Frobenius fixed points. So what makes this computable in cases such as ours is that Rathenauer-Scholze construct versions of motivic filtrations on all of these things, right? So we've seen in the first talk yesterday the story of motivic cohomology, and this fits in there. There's like a variant of motivic cohomology that filters TC. So concretely, the ith associated graded shifted down by 2i degrees of this sequence looks like this, where the thing that filters TC is symptomic cohomology, and then the other two terms are filtered by variants of prismatic cohomology. There's some twist involved and some completion, but it's essentially prismatic cohomology of R and the ith stage of the Nygaard filtration on it. And you still have Can and Frobenius maps here. So again, this is some kind of Frobenius fixed points. And now the thing that really makes K-theory, in this case computable, is that for a ring such as Z mod p to the n, or more generally, OK modulo some power of the uniformizer, where K is some finite extension of QP, we have that these two terms You can see this in various ways, but these two terms are concentrated in a single degree. They have only first cohomology for I bigger 0. So in the case I equals 0, there's also like 0th cohomology, but in this case, it's really all concentrated in cohomological degree 1. So homological degree -1. And so this equalizer here, in those cases, really has only H1 and H2. And what this tells you is that with the proper shift of 2i, this is concentrated in degrees 2i minus 2 and 2i minus 1. So somehow, at least if you care not about the spectrum K of R, but just about its homotopy groups, combination of these results tells you that they're all just neatly computed by individual symptomic cohomology groups because these somehow don't overlap. So in general, if you filter something and you understand the associated graded, there's still some kind of spectral sequence to run. But in this case, it all degenerates and you can just read off the homotopy groups of K theory. So how do you approach this thing here? Well, sure I can get. It's visible at once. Oh yeah. So how do we approach this thing? Well,
so zero symptomic cohomology doesn't only in degree.
Yeah, only in weight 0 does 0th symptomic cohomology contribute here. So this absolute prismatic cohomology that features here, nowadays there's like ways to understand that directly in terms of prismatization, but originally this arose really as an associated graded of some filtration constructed on these topological theories. And then in later work, Butt and Scholze recast this in some algebraic fashion. And it's controlled essentially through two properties. Well, first of all, this prismatic cohomology of, say, R quasi-symptomic has quasi-symptomic descent. And so, for example, this allows you to reduce computation of this to some quasi-regular semi-perfectoid things, like quotients of perfectoid rings by some regular sequence. And if R is quasi-regular semi-perfectoid, then if you just pick a perfectoid ring, S, with a surjective map to R, then Butt and Scholze observe that you can express this absolute prismatic cohomology as some kind of relative version where you work relative to A inf of this perfectoid ring, so bit vectors on the tilt. And this relative version, that's what they are just able to describe explicitly in terms of this prismatic site. But of course, a priori, there's a lot to prove here. Like, it shouldn't be obvious that this doesn't depend on the choice of S. So Let me just stick to 2 bolts. So this relative version is actually much more directly computable, because in nice cases, it's really discrete. It's only concentrated in degree 0 and thus given by like ordinary algebraic objects, nothing derived. And what is this based on? Well, let me remind you. So this is based on the notion of delta rings. So just quickly remind everyone what these look like. A delta ring is a commutative ring A with some operation delta, and this is not additive or anything, but still some kind of polynomial operation that interacts in a controlled way with both addition and multiplication. So for addition, you have some correction term by x to the p plus y to the p minus x plus y to the p over p. So this is, I guess, the first bit polynomial or something like that. And for multiplication, it almost looks like it wants to be a derivation over the p-th power map, but of course the p-th power map is not a homomorphism, so there's some correction term here as well. And the only way to remember these two things is to just remind yourself what we're actually after here is another operation, namely x to the p plus p delta x. That defines actually a ring endomorphism of A once you have these two properties. And this is giving a lift of Frobenius. And conversely, if you have a torsion-free ring and you have a lift of Frobenius, you can recover delta as like delta equals this. And now the base coefficients in this relative theory of Bad Scholze, that's given by prisms. So a prism is a delta ring with additional structure, namely an ideal, which is supposed to be Zariski locally principal on a non-zero divisor. So locally supposed to be principal on some element D. And this element is required to be distinguished. So what does that mean? Essentially means two things. First, delta of it is supposed to be a unit. And secondly, A is derived p comma I complete. And in all the cases we look at today, this ideal is really just globally principal. So in all the cases we look at today, we really can always pick like a choice of D, and then this is really just saying delta D is a unit and A is pi complete. Okay. So why am I saying that this relative version is more computable? Well, one particularly nice case. So maybe, sorry. one thing I wanted to say here is what is even the format of this relative version? This relative version takes a prism.
Then you write locally I is equal to this, you make some localization, then you write delta D is an A star. This means after a localization, so one has to be precise which localization. I mean, you localize at the prime containing I and P, probably this would be okay.
Yeah, I think I'm saying there's a Zariski cover such that with like you have to say complete or something, such that on each of these localizations you can pick such a D, and then of course there's some things to prove that this is actually, it doesn't depend on which D you chose and so on. There's other characterizations as well, but I think this is the most useful for us today. So for a prism and some algebra over A mod I, the quotient by this ideal, Bhatt-Scholze construct this relative version, prism R relative A. So a priori, this really depends on having this prism structure, which is somehow maybe notationally not quite reflected here, but yeah. So, and of course, there's a version where you also allow R to be some non-affine thing. You can take a scheme. Let me stay affine for this talk. So I said earlier that this is more computable. In what sense? Well, I want to highlight one result from the Bhatt-Scholze paper, which is that, let's maybe for simplicity say that our prism structure is really given by a principal ideal. So you can pick some D globally, some distinguished element. And let's assume that R is not just any A mod I algebra, but really A mod D and then some finite sequence of elements. And I want this to be a regular sequence. Or more precisely, like Kosul regular, but yeah. So in that case, they prove that prismatic cohomology has some very nice universal property in this world of delta rings. It arises from your base delta ring A by making R1 to Rn divisible by D. And then again, PD completing. So what does that mean? So these curly braces are just denoting that you do this in the world of delta rings. So what does that mean? That means you adjoin freely some elements, A1 to AN, and then you enforce some relations, namely you make DAI minus RI 0 for I from 1 to n. You have to do both of these things in the world of delta rings, but one thing that they also prove is how these things look like, namely the free delta ring on those generators A1 to AN really is like a polynomial ring where you just adjoin AI, delta AI, and so on. And similarly, enforcing these relations in the world of delta rings corresponds to quotienting by the relations, delta of the relations, and so on. So this is a nice presentation of this, just that you have like infinitely many generators and relations. And then you can start computing around with this, right? And it's not super straightforward just because delta interacts in this awkward way with multiplication and addition. But in principle, you can evaluate all these things, see what you get, play around with it. And one thing we observed is that this doesn't really seem to care which prism structure you pick here. So in general, you could be able to pick different prism structures on A, so different D, such that R is still like an A mod D algebra. And one thing we observed just by playing with these prismatic envelopes is that it doesn't really seem to matter which prism structure you pick at all. And so one thing that we were able to construct is some kind of refinement or extension, maybe, of their theory, which we call prismatic cohomology relative to delta rings instead of prisms. And this takes the following format. So we observe this functor prism, which is defined on pairs of like a prism A and an A mod I algebra R, really extends to a functor on what we call delta pairs, which consists of A and R, where A is a delta ring and R is a algebra. Not asking for any distinguished element here or anything, just this data. Of course, there's also non-affine variants. You can take R to be just an A scheme. You can even take A to be like a delta scheme or delta stack. So there's variants of this. We're saying you can do this in much bigger generality. And in my mind, at least, this feels like a nice kind of blank spot, because as I mentioned earlier, absolute prismatic cohomology is constructed by Bad-Scholze in this kind of indirect way, where they observe that in like quasi-symptomic locally, you can define it in terms of relative prismatic cohomology, but then there's still some well-definedness you need to check because you have different perfectoid rings that you could pick. And so somehow relative prismatic cohomology and absolute prismatic cohomology are connected, but somehow in a slightly awkward way. This is like the missing link that connects the two. And how does it connect the two? Well, we observe if you let A be the initial delta ring, which is like Z with Frobenius lift the identity. I guess you could also just let everything be p-adic, and then you would take ZP, but it doesn't matter, like what we construct factors through completion. Then prismatic cohomology relative Z is just absolute prismatic cohomology. And if there exists some ideal I in A making A into a prism and R into an A mod I algebra, then this prism R relative A is just relative prismatic cohomology in the sense of Bad-Scholze. And this is somehow already useful, even if you're just working with relative prismatic cohomology, because this tells you that in situations where R is an A algebra, but you could pick different such ideals, right? So for example, if R is really such a quotient, then the kernel of the map from A to R could contain multiple distinguished elements, which are maybe not multiples of each other. So they really define different prism structures. This tells you that somehow all of these prismatic envelopes will somehow canonically agree. So this really gives you some additional factoriality on relative prismatic cohomology as well. Yeah. It looks tautological, but I'm just saying that, so this notation was taken to mean something in terms of a prism in like Bad Scholze. Maybe let me just put this decoration here. It's like relative prismatic cohomology following Bad Scholze. We're extending this to something more general. This is just telling you that the notations agree, like there's a potential confusion here, and I'm just telling you that it doesn't matter. Right. So this nicely explains some things, right? So for example, this gives you a really nice way to think about this fact that in some cases you can describe relative absolute prismatic cohomology through relative prismatic cohomology, because secretly this is also relative. It's just relative Z. And then there's an actual map, since there's like really a morphism in the category of delta pairs. And one of the things we check is that you still have things like Hodge-Tate comparison in this setting, but like Hodge-Tate comparison in the absolute setting. So there's like some Hodge-Tate filtration, there's like this diffracted Hodge thing, and all these things still in this language. And so you can just check that this map that we have is an equivalence just by knowing some things about the cotangent complex, namely using that Witt vectors of a perfect thing are like relatively like the cotangent complex relative Z vanishes. This is kind of a nice explanation for this phenomenon. But the reason why we were really after this thing and believing that it exists is, so we were motivated to try and compute absolute prismatic cohomology of rings such as Z mod p to the n in a way that is somehow still like finitary enough that the computations are possible to run on a computer. This was one of our goals, which we achieved. I'm going to tell you something about that in a second. And if you resolve by quasi-regular semi-perfectoid things, these are always like very infinite objects. But we were motivated by a paper by Liu and Wang, who observe that you can, on this topological side, compute TP of a ring by resolving it through relative versions. Where the idea is somehow you work relative one variable, but then next cosimplicial level you work relative two variables, and so on. And you get a limit diagram like this. And so you would hope that there's also a direct analog of this you can write down in prismatic cohomology, which somehow exhibits absolute prismatic cohomology as a limit of relative prismatic cohomology, where maybe we want to work relative something like, in this case, OK mod pi to the n, relative something like the Breuil-Kissin prism. Right, we just have like a power series ring over Witt vectors, and then the distinguished element you could put on here is like an Eisenstein polynomial. And then the next stage of this cosimplicial diagram that you would hope to write down is something like a Breuil-Kissin prism in two power series variables, But then you run into a problem, right? Like, how do you make this into a prism? You could pick like the Eisenstein polynomial in Z0. You could pick the Eisenstein polynomial in Z1, but these are different prism structures. And so a priori, you only get one of those two maps after making a choice here. And so one thing that our extension here achieves is that you can really just write down this diagram.
Sorry, so in the case where you have two prism structures, like let's say the two distinguished elements are D1 and D2, what's the relation between prism R over A and prism R over A adjoint D1 over D2?
Say again, prism. Sorry, what were the two?
I'm asking in the case where there are two distinguished elements, there's a universal way to make one divisible by the other, and then they become units there. So then you could also be in a setting of usual prismatic cohomology, and I'm asking if that usual setting is related to the relative theory you're.
Ah, yes, yeah, okay. That's a good question. Yes, that is a fair point. Like, I find this very satisfying, but there is a way to obtain the same diagram just in terms of usual prismatic cohomology by observing that you have some base change properties that tell you that this prism R relative this actually agrees with something relative some prismatic envelope here, right? This itself is somehow a prism in an awkward way, but there is a coproduct of two copies of the Broyles-Kissin prism in the category of prisms, and it takes this kind of form. It's itself a prismatic envelope. And then you can also base change R to that thing. I think that answers your question, right? So this diagram that we constructed is secretly also the thing that you get from like covering W card by like spiff of the Broyles-Kissin prism. But for psychological reasons, I find it easier to think about this type of thing directly as a prismatic envelope because it doesn't involve the space change and yeah. Okay. So this actually works. You do have this kind of descent, you do have this limit diagram, and there's also like a Frobenius twisted version of this, because there's this slight awkward thing that like absolute prismatic cohomology just carries a Nygaard filtration. Relative prismatic cohomology does only carry a Nygaard filtration after Frobenius twisting. And so we do have this diagram, but the one we actually care about more is the one where you put a Frobenius twist here. And then you have a Nygaard filtration, and the Nygaard filtration is also compatible with this limit. So this gives you a way to compute absolute prismatic cohomology with the Nygaard filtration in terms of things that you can express as prismatic envelopes. And so in particular, you get a description of the symptomic complex really as like fiber of such a complex, like of can and phi maps between two such complexes. So for R given by OK or OK mod pi to the n, right? I guess these are the only two interesting like quotients of regular quotients of OK. So we can write this as some total complex. And the additional thing that we have available in this situation is really, like I mentioned earlier, there is this cohomological dimension observation that like all the prismatic cohomology for these things really lives in, like has only up to H1. And so this tells you that you should be able to just truncate these complexes that you get here to just two-term complexes, right? There's not going to be higher cohomology. So you can truncate these complexes to something where you maybe just took like the kernel of the next differential here, and then they really become two-term complexes. And so you should expect a square where here you just work relative one variable. You have the can minus phi map here. And sorry, there should be like a Breuil-Kissing twist here. All these things like work with all kinds of decorations. And then here, maybe a priori, you want to put the kernels of the maps that go out here. But one funny thing we observe is that you can interpret the differential you're getting here really as some kind of connection. So what we actually write this diagram as is there's a slightly re-indexed version of, again, prismatic cohomology relative one variable. And some kind of connection here. And here, again, a version of can minus phi, but somehow in the identification where we identified the kernel here with like some twisted version of prismatic cohomology relative one variable again, we somehow incurred some funny twist here. So let me call this map like phi nabla. Let me maybe say this, so this doesn't look as mysterious. This term is like non-canonically isomorphic just to prismatic cohomology of R relative the Breuil-Kissing prism. And you could put like a Breuil-Kissing twist here, but somehow in this setting, the Breuil-Kissing twist can be trivialized away. And I'm saying non-canonical here already, so I'm not quite sure which twist I want to put here. So there's some non-canonical identification, but what happens is that somehow the Nygaard filtration gets shifted. So that's why we put this nabla decoration here. And also under this identification, the action of the Frobenius here becomes somehow like some funny map. So we have a different name for it. But it really tells you that you should think of absolute prismatic cohomology as fiber of some kind of connection, and the symptomic complex as total complex of some square. So, as I said, our original goal going into this project were computations. And these things, they can all now be described in terms of some prismatic envelope. But of course, as I said earlier, these are like countably presented. So if you really want to just do a computation and really get some abelian groups out in the end, that's still not finite enough. So there's some additional observations we make. For example, we observe that all of these terms inherit filtrations, which come from the z-adic filtration on this Breuil-Kissing prism. So one thing we observe is that this additional factoriality coming from prismatic cohomology relative to delta rings allows you to construct filtrations on prismatic cohomology whenever you have like a filtered delta pair. So you need a filtration on R, filtration on WK joint Z, and the filtration on your delta ring needs to be compatible with delta in a way where like delta FKA is contained in FPKA. That's the type of thing that we only know how to make in this Broyle-Kissin situation. So I think this type of connection is much better understood if you work relative to the Q-de-Rham prism, but somehow this crucial ingredient of a filtration that somehow makes our problems finite, we don't think that we have that in like a version of that in the Q-de-Rham situation. But let me just say, so we have these filtrations, and then we prove that the symptomic complexes have bounded filtration. And so that allows you to kind of truncate all of the terms in this square to some finite filtration, and then all but finitely many of the terms in these prismatic envelopes fall away, and you can really reduce this problem to linear algebra and compute with it.
Achim?
Yeah.
What happened to the degree 2 and higher in this cosimplicial?
Right, so in the original cosimplicial diagram, I would have put something where I've worked relative WK adjoint Z0, Z1 here. And then there would be like another differential, which goes to like the thing relative WK adjoint Z0, Z1, Z2, and so on. And I know that the cohomology of this complex is concentrated in degree 0 and 1. So I know that I can just replace the complex by the term where I just put the kernel of this map in degree 1. And what I'm telling you here is that that kernel itself can somehow be non-canonically identified with a slightly re-indexed version of the thing where I work relative 1 variable. So this makes this really into a square. We have these bounded filtrations. We can compute things. We can also make some conceptual observations. For example, we observe that H2 of these squares vanishes for large enough I. Maybe I want a twist here as well, sorry. So we observe.
The boundedness from the OK mod pi to the f case or also for OK?
For OK mod pi to the n. Good point, yes. And the bound is something like in minus 1. Right. So we also get a result just by hand from this, which we call the even vanishing theorem, which tells you that K theory of OK mod pi to the n vanishes for large enough I. It's kind of a nice observation that you can make from these squares. But so what I wanted to get to today, and let me talk about that in the last bit of the talk, is where does this weird connection come from? Because I think people who maybe are less interested in computing like the 41st K group of Z mod 32 or something might still care about what this type of connection here is, because like there are versions of this that people have investigated in I mean, there's classical versions of this, of course, in crystalline theory, but there's also versions of this that have recently been investigated over like the Q prism. Like there's this paper by Gros, Storm, and second. 0, where they do like some version of nabla of this connection over q minus 1. And somehow in this picture, you really get some nice looking formulas. It looks like you can do some calculus with these things. In the Breuil-Kissing situation, we still don't fully understand what's going on. But let me just tell you like about a general source for these operations and this one-dimensionalness. So let me start by just kind of abstractly looking at a cosimplicial diagram of rings, such as the ones we get from this descent. So in a very happy situation, this would maybe just be some kind of check complex. But one thing that happens quite a lot is that this is not literally a check complex. You can't write this as a tensor product of gamma 0 with itself, but where you can express all of the diagram in terms of gamma 0 and gamma 1. So call such a diagram one co-skeletal if all of the maps from gamma n tensor over gamma 0 with gamma m to gamma n plus m that you get out of such a diagram are isomorphisms. So this somehow identifies gamma 2 with gamma 1 tensor gamma 0, gamma 2, and so on. You of course know that you get such a diagram whenever you cover a nice enough stack by some scheme, like you've seen this before. There is an algebraic way of thinking about diagrams like this, which I think is probably more familiar to algebraic topologists, which is the structure you have on gamma 0 and gamma 1 that allows you to describe the whole diagram here is something that algebraic topologists call a Hopf algebroid. Because it's kind of like a non-commutative, it's like a version of Hopf algebras. So you have like two ring maps from gamma 0 to gamma 1. We call these eta L and eta R, but of course these are just D0 and D1 in the cosimplicial complex. You have some kind of co-multiplication coming to you here is the middle map, and together they satisfy various axioms. So this is like a Hopf algebroid. But of course, the algebraic geometry perspective on this is probably like it's a groupoid object in affine schemes. This is like formally dual to what a groupoid object is. So whenever you have something like that, there's a way to define, like to construct something like differential operators just by dualizing gamma 1. So gamma 1 here has a has two ring maps from gamma 0. We think of these as giving you a left module structure and a right module structure on gamma 1. These are different, but you can look at like the left module dual of gamma 1. It's like left module maps. And for any such left module map, you can form a composite where you take the second ring map, like the right module map from gamma 0 to gamma 1, and you post-compose it with this. So this is now just an additive map. You lost any linearity by combining these two things. Let me call that map nabla theta. And more generally, there's a notion of comodules over such a thing, which geometrically corresponds to quasi-coherent sheaves on the stack presented by such a diagram. So these are things with, you could say, right modules with some kind of coaction. And on things like that, you can still compose with this map theta to obtain some kind of action like this. And actually, there's a bijection between natural operations on such comodules and just elements of this dual. And one example that I found very illuminating, thinking about these things here, and thinking about what to expect of this nabla and so on, is the following. If you let gamma 0 just be, say, a power series ring in one variable, gamma 1, a power series ring in two variables where you also adjoint divided powers, k some base ring. Of course, if it's characteristic 0, then the divided powers don't change anything. And now take the elements Bn, like z1 minus z0 to the n over n factorial. These form some kind of completed basis of this as a left module. And so I can define maps theta n, they're like dual to this basis. And then if I unwind what all of that means and how to think about these operations nabla, I get that this eta R map, which takes z to z1, fits into an infinite sum like this, right? By completeness, this is something I can form, and this somehow follows from the fact that this is like the dual basis to this. And now, what is this? Well, this here is just z1 minus z0 to the n over n factorial. This here just is like a power series f with z1 substituted in. And here we have some operation applied to f. And then we, like this is using the left module structure. So this has like z0 plugged in. And of course, what is it? Well, it has to be the nth derivative. And what I'm writing down here is just Taylor. So this formalism somehow lets you think about versions of this if you don't quite have divided powers. And that's the situation we're in. So am I out of time?
5 minutes.
5 minutes. Ah, that's plenty. Okay. I wasn't sure whether it's 50 or 60. Very good. So what's the situation we're in? Well, we're actually in the situation where R is maybe some OK algebra. And our descent complex thingy from earlier arises. It also satisfies this one co-skeletality condition, essentially from the fact that in prismatic cohomology relative to a prism, you do have some kind of Kyneth formula, and all of the higher stages of our diagram are really things where you can interpret them as prismatic cohomology relative to a prism. So here, our base thing is just prismatic cohomology relative to the Breuil-Kissen prism. And the stuff in cosimplicial level 1 is the thing relative to two variables. And let's maybe focus on just the case R equals OK. And in the end, I can tell you a little bit about what you can do for a general OK algebra. But in that case, this here is just A mod I, right? This is just the quotient of this by the Eisenstein polynomial. this thing, that's a quotient by two things. You quotient first by the Eisenstein polynomial, but then you also have to identify Z1 and Z0. So by this prismatic envelope description, if I didn't have a Frobenius twist here, this would be this thing adjoint, like making Z1 minus Z0 divisible by the Eisenstein polynomial in the world of delta rings. So you can get some kind of description like that also on the Frobenius twist, of course. What we find is that there's like a better presentation that you can get out of that by massaging it a little bit, and namely one that's also compatible with the Nygaard filtration. So what we find is like one of the main ingredients in our computation is that this also admits a presentation where you adjoin elements G0, G1, and so on. And there's no Z1 here because like the G0 is actually Z1 minus Z0. And then you quotient by a sequence of relations. And these relations we provide some explicit formulas for in terms of like some recursion that involves the operator delta. But they're of the form minus p plus some unit times d to the p to the j plus 1. D is the Eisenstein polynomial times gu plus 1. So far, this looks like some kind of divided power thing, but unfortunately, there's also a second term, which kind of makes things more complicated. But this is like a polynomial in these g's as well. Sorry, j, not u. So we find some presentation like this, and you can compute with it, but you can also qualitatively notice that this allows you to express p powers of your generators in terms of other stuff. So one thing that this implies is that, maybe let me put this here, as a left module over this, this is like, this has a basis in a completed sense on products, on monomials, where all exponents are smaller than p, right? And this now looks very much like what you have in p-typical divided power algebras, right? Because the divided power algebra is somehow also generated in a similar way by like monomials in the p-th divided powers. But of course, it's not literally a divided power algebra. It does become a divided power algebra if you quotient by this element d. And there are some versions of this connection that we construct that you have modulo d, so on the Hodge-Tate locus. So we expect the thing that we write down to be a deformation of this sen operator that you have in that situation. So this is not a divided power algebra. We can't quite do the thing that I did in the example earlier, but of course you can still just take that basis. It feels a little bit ad hoc. That's why I said earlier there's some kind of non-canonical identification, but we have this basis. So nothing prevents us from just taking a map theta, which is defined by taking G0 to 1 and all other such monomials to 0. So this is like the dual basis element of G0. And then just again passing to some associated differential operator like this. But what does it entail now to compute how this acts? Well, for example, just in this case, on gamma 0 itself, right? This is wk adjoint z. If you want to compute how this acts on some monomial z to the k, you first have to figure out what happens under the right map, so the one that takes z to the like to z1. That takes it to z1, which is like G0 plus Z0. And then you have to apply this map theta, which extracts like the coefficient in front of G0. And in the usual divided power setting, somehow you really have like a monomial basis where if you multiply two of the basis elements, you just get a higher basis element. And so then it's easy to tell what the leading coefficient here is. It's going to be something like k z0 to the k minus 1. But here, these terms will also involve G0 in a linear way. So there's like a lot of correction terms here. So this acts in a subtle way. And I would love if we had some kind of symbolic way to compute with this currently. But like the way we do it in our program is, since we only care about stuff up to a certain filtration, we really just brutally rewrite this thing using these relations and then just look at the coefficient. Nevertheless, I can prove that this thing does satisfy some kind of Leibniz rule. You would hope for it to be an actual derivation maybe, or maybe not. I mean, with this thing that is known over the Q prism, you also have to massage this a little bit to be true. I can prove that you get some Leibniz rule where you have higher powers of this operation appear here, possibly an infinite sum. We're working in some complete setting here. But I guess I don't currently know how to write this down in like a closed form description. Of course, by like the very nature of what we're doing, we are able to compute what's going on here up to some finite filtration. But it would be nice if there was some explicit formulas in terms of the distinguished element and delta and so on. Right. So yeah, let me maybe stop here.
So you mentioned that if you tried to do this with the Q prism, you would have run into some problem with making the filtration compatible with Frobenius. I don't know, can you elaborate on that?
Yeah, so I mean, the filtration on WK adjoint Z, here we take the Z-adic filtration, and it's compatible with the Frobenius just because phi of Z is Z to the P. And so the behavior we need is that phi takes f bigger equal k into f bigger equal pk, and so you have that here. But for the Q prism, take something like ZP adjoint Q minus 1, you can't take the Q-adic filtration because Q is invertible. And if you want to take something like the Q minus 1 adic filtration, you run into the problem that phi of Q minus 1 is Q to the P minus 1, which is only divisible by Q minus 1 once. So it doesn't have this property. And so as far as we understand, these filtrations are really a phenomenon that you don't have here. Maybe there's a way to tweak it, I'm not sure, but currently it seems that that's like the main computational benefit that you have on the Broad-Kissin side. Yeah?
One of the asymmetries is that atomic cohomology, for example, exists in this relative thing relative to any delta ring. Do you think at all whether motivic cohomology over Z it can exist relative to something?
It would be cool. I don't think I have any intuition for that. You can
I
probably...
think I have a proposal definition relative to GM, or the power of GM.
Right.
But I'm not sure whether it matches your p-adic story. So.
Right. I mean, I think so somehow, since you can talk about, like, I think since like you get canonical delta ring structures on the p completions of lambda rings, you can, for example, write down some integral, like some pro-finitely complete thing relative to a lambda ring. But this is just kind of a stupid product, and I'm not sure whether, like, how to make this integral. Yeah.
Sorry, what was the proposal?
I mean, I think, right, on the way to some kind of integral version of this, you might first think about, well, can I now combine different, like, can I do something that's like p-completing to prismatic cohomology at different primes? And one stupid thing you can do is, if you have a lambda ring A, then each of its p-completions has a delta ring structure, and you can write down something like prismatic cohomology relative to A that completes to the p-adic story at every prime by just, I guess, taking like a product or something. But I'm not sure whether there's like a good integral version. Yeah, okay, I'm not sure. Seems that lambda rings maybe play a role, but I'm also not sure. Like, we haven't really thought about it, but maybe there's some version of prismatic envelopes where you use a lambda ring structure, but I guess I'm not sure about that. Yeah, don't think I have a clear proposal. Yeah.
What is the relation of the Ninabla and the Frobenius? Is that a commute somehow?
No, it interacts in a complicated way. So there's somehow two things you can produce. You can produce the thing that I've written down here, which acts on Frobenius twisted and possibly Nygaard completed relative cohomology, prismatic cohomology. And then you also have some version of this without the twist. This arises from like a different basis that we can write down. And we can say some things about some compatibilities here. You have like two maps. One is the like relative Frobenius. Goes from here to here. And the way we chose that basis, somehow this diagram really commutes. If you say it correctly. But then the other map, right, there's also a canonical map from untwisted prismatic cohomology to the Frobenius twist. That just does something completely different. So yeah, with the composite, which is the actual like absolute Frobenius on this thing, it interacts in a complicated way. Yeah, potentially there is also some kind of compatibility in terms of power series like that, but I'm not sure whether I can, like, don't currently know what to do with that.
Right, let's think.